Thank you. Thank you for the introduction, and thank you all for staying. And this is one of the projects that is done in collaboration, CTU in collaboration with Avast. And we're going to be talking about the problem of malware classification and our tries to approach it as a continual learning problem. So my name is Rigaki.
And I'm Elnaz Babyeva.
But this work was done also in collaboration with two more people, Sebastian Garcia from CTU and Peter Gronat from Avast. So a few words first about the motivation. Why do we want to do this? So as other speakers already said, malware evolves in a natural way. First of all, malware authors try to change the malware. They add more features, they change compilers, they change a lot of things. But more importantly, they try to evade detection of any kind. Machine learning detection, more classical approaches, YARA rules, whatever is out there. That's their job, after all. So if you try to use a machine learning model to actually classify malware families, and the malware changes, that means that your model performance will degrade over time. It's expected because there's some phenomenon called concept drift. The data changes, so you're detecting the wrong thing after a while. So sometimes we hear researchers, but also in the industry, there's a strong assumption, OK, our model degrades. What should I do? I will get the new data, and I will retrain with whatever I have and update the model. And while this might be working, it still gives us some constraints that we have to consider, because you cannot keep retraining forever with all the data you have. You cannot expand your models infinitely. You cannot expand your memory infinitely. You should do some, maybe select which data you're going to use to keep training. But then, how are you going to select them? So there are a lot of questions. So our idea is, if we assume that models degrade, can we do something which is effective, and more effective at least from just retraining with all the data? So our approach is based on the continual learning approach, which in the past few years revolves mostly around neural networks, but the main ideas are borrowed from the way humans learn. So a very simple definition of continual learning is the ability to learn something without forgetting what you have learned in the past. When we're children, for example, we learn how to bike, hopefully. And then at some point, we might learn how to drive. This does not interfere with our biking potential, hopefully. We still remember it after years, or at least we might be a little bit wobbly, but after a few spins, we can still do it. So we would like models that do something like that, right? What are the goals, as at least most of the researchers have put in continual learning systems? First, as I said, do not forget the past. Second, we should be able, as you learn new data, sometimes humans also will learn something new, but it reinforces some of the old things that we knew. And also, it will ideally, if you learn something, you would like this to transfer the knowledge and help you learn faster in the future. The third kind of goal is that all the systems assume a fixed memory footprint. So we don't want them to increase infinitely, because we cannot actually sustain this. And there is a fourth goal, which is more like a wishful thinking, if you ask me. You might have different tasks that you learn after another, but sometimes the tasks are not easily discernible between each other. There are problems that are not easy to detect when we pass from one task to the other. So I don't think we're there yet, but ideally a continual learning system should be continually improving and keep working. So when we started, we posed ourselves 3 questions that we will try to give you some initial answers today as well. First of all, is this approach actually useful for malware classification? Because it's not a given. It sounds like a good idea, but how do we know if we don't test? Second, can we learn these new families, but without forgetting the past? And then third, if we do, can we do it in an efficient way in terms of speed, the storage, and memory, and so on? So when we talk about continual learning, there are 3 major categories of research that's going on, and papers. So the first one is regularization method. So briefly speaking, for those that are not machine learning researchers, and that's probably some of you here, in regularization, the idea is that for these models, the neural network doesn't change, but the way from one task to the other, we change the parameters of the network, the weights, depends on how different the tasks are. Okay, just briefly that. Then there is the approach of the dynamic architectures, where some people propose to actually expand the networks and add more hidden units or add more layers. So this accommodates the new knowledge while retaining some parts from the old kind of the idea to be able to do well in the past tasks. And the third part is some systems that they propose, like the humans have like long-term and short-term memory, to have some sort of memory, not a lot, not all the data, a little bit of, a few of the data samples for its tasks that will help us not forget. So very, very briefly, I will talk about two methods that we tested. That's why I have to present them a little bit so you understand what the difference is between them. So the first one is called elastic weight consolidation. This is considered one of the state-of-the-art regularization methods, so it's in the first family. And they just try to do what, as I said before. So when you learn a new task A, and when you learn the task B, if the weights of the task B are very, very different from the first task, you try to actually constrain this difference, because you don't want, if you change your neural network completely, then you will not remember, and you will not do well in the past classification problem. And the second method that I will introduce is called gradient episodic memory. So it has the memory component, which is a few data points from the previous task, very little. And it has a second kind of idea, which is now we're not looking at the weights themselves, but we're looking at the direction of the change of the weights. Think of it like speed and acceleration. So we're looking at how, if in task A we change towards this direction, and then task B tries to change them in this direction, that's kind of favorable. The angle is not very, very big, so we have knowledge transfer. But if we are in the case where one task wants to go in this direction and the other is totally diametrically opposite, then that's not good. Then this is where forgetting happens. If we allow this to happen and the weights move in this way, then we might forget. So what they're trying to do is to devise a method that projects this vector closer. Okay? The problem with this method is that it's very costly. They devise an optimization algorithm, it works, but as the number of tasks increase, then it takes more and more time. So for this reason, we decided to test, okay, what if we don't use all the tasks that we have available, but we use only a fixed number of tasks every time, like a sliding window? And let's see if that works. And you will see the results later and find out.
Yes, and when we started to do this research, we found out that we need to have the datasets. And during the research, there was no publicly available datasets with different families, so we decided to create our own thanks to Avast databases and systems. So we created a malware evaluation set dataset, MESS, which consists of 5 families. The data was collected from May 2018 to March 2017. We have timestamps for each sample, and all the samples were defined by Yara rules. This is the rules which based on patterns. We chose these 5 families because they're quite different from each other, and we have 2 versions of datasets, MESS v1 and MESS v2, where in MESS v2 we removed all the samples which look like packed malware. This is a distribution of our samples in our timeline. So different families are visualized in different colors. In blue, you see the month splits, and in colorful bar plots, you'll see the week splits. We have 60 of them. And as you see, the malware is acting differently during the time. So first, we have from March to September, the Xpero was really popular, then Romney was taken over, then WannaCry and Redux. And the second dataset, which we tested, was Ember dataset. And Ember has also 2 versions, 2017, which has 1 million binary files, only information about months, but it didn't have any family classification. So we had only malware, benign, or unknown. That's why actually we created our own dataset. But in late August this year, Ember got a new version of Ember 2017 with also 1 million new files, only, again, monthly time splits, and about 3,000 families of malware. Okay. And this is a distribution of samples in time. So it's from January 2017 to October 2018, sorry. And the advantages of the mass dataset is, comparing to Ember, is that for mass, we take all available samples from a vast system from one specific error rule for a given time period. While in Ember, we didn't know how they chose samples and selected families. And this is our experiments. We did two types of experiments, class incremental learning, where in each task we added a new family, and learning in time, when we split the data in time windows of different sizes, monthly or weekly. And we have 5 models to compare. So first one is baseline multilayer perceptron. It's small neural network. And the second one is full memory multilayer perceptron, which actually is like Oracle method because it's trained on all the data which we've seen before. And then 2 methods which were presented by Mari is EWC and GAM, and our proposed method as GAM. But continual learning is not a typical machine learning task, so we have to choose a matrix which we are going to measure. So in our case, it's 3. It is a mega new, which measures how well we are doing on the new data. A mega back, it is how much the model remembers, so how well we are doing on the past data. And a mega new is how well we are doing on not seen data, so in the future. But before showing you the results, I want to show you the problem of baseline solutions. As you see here, this is a behavior of the WannaCry with all 3 metrics. And from September to May 2019, WannaCry is predicted pretty well. But even though it is predicted well by the multilayer perceptron, also we forget a lot the past data. So this is a problem of MLP. And similar is happening with StreakBot. We see that we are doing pretty good from May to October, but we do not generalize at all for the future data. So the future data is so different, as we were saying, that malware involves, so we are not doing good at all. And this is our results. So as we see, for new data, all the methods are doing pretty good, and I believe that it's happening because in each task, in each time windows, weekly, we have a small amount of data. But all the continual learning methods, outperform the baseline solution. And we also, with GAM and SGAM, outperform the full memory MLP, which have all the data stored and retrains on data over and over again. And surprisingly we got much better results for future unseen data. But as we see, GAM was really, really slow.
Yeah.
Okay, I think I ran out of battery. So GAM is really, really slow. And we, with SGAM method, we improve it almost twice. The similar solutions we were doing, the similar experiments we were doing with Ember top 5 families dataset, and we see that for orange, orange is a backward score. We don't decrease so dramatically as a baseline solution. We decrease much smoothly. And the same is going on with Omega forward. We grow much faster than a baseline solution. So to conclude, we had 3 questions to ask, and we tried to answer all of them. We believe that continual learning is a promising avenue. Also, for new data and for future unseen data, we are doing pretty good and even outperforming a full memory MLP. Also, we have a good performance of continual learning method for the past data, but with GAM and SGAM, but not so good with EWC. And again, as we told, GAM is slow, and we already increased it by SGAM method, but we believe that we could do much more experiments with this. And it's actually work in progress, because we're currently working with much number of families, so we are working with 70 families. looking into a way how we could speed up these memory-based models and also increase the number of tasks, so increase the time periods, like time spans. That's all. Thank you.
Thank you.